Okay, so let's say we want to now move on to drawing a tripeptide, and keep in mind when we have tri here, or di, or tetra, penta, whatever we have here, it tells us the number of amino acids contained in this polypeptide chain. So in our case it says tri, so we have 3 of them, and we have the 3-letter codes here: his for histidine, gly for glycine, phe for phenylalanine. And let's say we want to draw it at a specific pH, which we'll say pH of 10. So what we would do first is we're going to draw our tripeptide with all of its hydrogens present. That way we would not have to have a struggle of figuring out who is being lost, which hydrogens are being lost, and we can just have a good starting place. So we would start off with, since histidine is first, we want to draw our histidine. So here's our histidine, here's the side chain for histidine, going up to the C double bond O. This right here is our first peptide bond connecting our histidine and our glycine. So now the N-terminus for glycine, the alpha carbon for glycine, the side chain, the carboxylic acid for glycine is now peptide bound to the N-terminus for the phenylalanine, or the amino N. Next to the alpha carbon for phenylalanine, its side chain, and then we end with the carboxylic acid for phenylalanine, because that is the end. Those are our 3 amino acids. We don't have to make another bond, so that's why we see this one here. So what I also went ahead and did was I wrote out where our pKa values are going to fall, which hydrogens they are corresponding to. And since I'm not sure if you have your charts with you at home, I wrote out with the information the chart gave us. So for histidine, we had 3 ionizable protons at pKa1, pKa2, and pKar, while glycine and phenylalanine only have 2 values for pKa's, which means their side chains cannot lose a hydrogen. That being said, I wrote out where they would fall in our fully protonated structure of our tripeptide. So here is 9.2 representing the amino terminus for our histidine. The 9.2 corresponds to that pKa2 of histidine. Then, because histidine has a pKar value, that 6 is corresponding to the hydrogen off of this nitrogen. Keep in mind it's not off of this nitrogen. Why? Because this nitrogen already has 3 bonds. Nitrogen does not like to have 2 bonds, so it will not lose a hydrogen. The nitrogen over here has 1, 2, 3, 4 bonds. That's why it has a plus sign, so he is happy to get rid of that hydrogen over there. So that's the 6. There is no ionizable proton at all for glycine. Why? Because his amino terminus is involved in a bond, so it's not going to lose any hydrogens. And his C terminus is involved in a bond, so it's not going to lose any hydrogens. And its side chain does not have an ionizable proton. When we go to lastly phenylalanine, which we have here, phenylalanine, again, its N-terminus is involved in a bond, so it's not going to lose a hydrogen. Its side chain does not have an ionizable proton, so the only hydrogen we can lose for phenylalanine is the hydrogen off of the carboxylic acid here, and that is corresponding with that 1.8 that we saw from our chart. We can then move on to actually drawing this at the specified pH that the problem asked, which was pH of 10. So since 10 is greater than every one of the pKa values that I wrote out here, then that would mean we would lose a hydrogen from every one of those positions. So doing so, it would look like this. We lost the hydrogen from the amino terminus here, therefore there is no more positive sign. We lost the hydrogen from the R group of histidine here, no more positive sign. And we lost the hydrogen from the C terminus side of the phenylalanine, and we put a negative next to the oxygen. In doing that, this is the structure of the tripeptide at pH of 10. We can also go farther and figure out the PI of this tripeptide. And in order to do that, it's very helpful that we've already drawn the fully protonated structure of the tripeptide and the fully unprotonated structure of the tripeptide. We know the net charges of these guys, so for our fully protonated structure of our tripeptide, it has a net charge of +2, which came from that positive sign off of the N-terminus of histidine, the positive sign off of the R side group of histidine, and then the fact that we have no other charges. So it has a +2 net charge. Our fully unprotonated does not have a charge here, and it only has a charge at the C-terminus side of phenylalanine, giving us a net charge of -1. Therefore, if you were to just write out a little structure for yourself to figure out how this thing goes from fully protonated, which you found had a net charge of +1, to fully unprotonated, which has a net charge of -1, you all know it has to go step by step, so you just count down. So we have +2, +1, 0, -1. It's like a number line. Then you just fill in the pKa values in between each one of those numbers. So we start off in order. Please keep in mind it needs to be in order from the smallest pKa value to the largest pKa value. So we did the 1.8 followed by the 6 followed by the 9.2. In order to figure out your PI that you have here, all you have to do is find where you have a net charge of 0, use the 2 pKa values on either side of that net charge of 0, plug it into the equation, and you get your PI value.